Good morning, everyone. Thank you for tuning in to the Urban Water Innovation Network Science Talk webinar series, which specifically focuses on key findings of the research projects with an emphasis on implications of the results and pragmatic recommendations for stakeholders and practitioners. Today, we will continue exploring Research Thrust A with a presentation from Dr. Elie Bou-Zeid. I'm also thrilled to note we do have some stakeholders joining us today from across the country, so we really appreciate your time this morning and are looking forward to hopefully a fruitful discussion towards the end of the hour. Also be sure to tune in next week for Project A22, Modeling the Metropolis, Projecting Future Environmental Change in Urban Areas, which will be presented by Dr. Mate Georgescu at Arizona State University. As you probably noticed, we are recording this webinar and we'll post the videos to our YouTube channel and UN website, and I'll be sure to drop that link in the chat queue as well. Participants should have entered muted, so please pop your questions in the chat queue, and barring any technical difficulties, you can also raise your hand at the end of the presentation and we can connect you directly with our presenter. So with that, I'm excited to introduce Dr. Elie Bou-Zeid, Professor of Civil and Environmental Engineering at Princeton University. Dr. Bou-Zeid's research focuses on the integration of theory, numerical simulations, and experimental observations to study flow and transport in the lowest layer of the atmosphere where humans live and have direct impact on the planet. His work extends from the fundamentals of turbulent flow and heat transfer in that layer to various applications, including the built environment and its environmental quality, energy efficiency in buildings, urban sensor networks and their design, wind farm design and wind energy forecasting, and surface atmosphere exchanges over fractured polar ice seas. So with that, I'm going to hand it over to you, Elie.
Thanks a lot, Sarah. Thanks everyone for being here. So I'm going to give kind of a quick recap of what Project 821 is about. And then I'm going to tell you basically what I learned through my work on this project in much more kind of practical way. So for those of you who are part of UN or who have been following UN for a while, the overarching hypothesis of this project, interactions between the atmosphere, the surface, and the subsurface are important drivers of hydrological dynamics over and atmospheric dynamics over urban terrain. And therefore, models should really capture these interactions and not try to model, let's say, the atmosphere and the subsurface separately. And this coupling is important to basically develop measures to mitigate heat or extreme flooding in cities. The aim of the project was thus to integrate the wide range of expertise in UN SRN to achieve groundbreaking advances in our ability to model individual component of the urban system, as well as the integrated system itself. So the integrated system was an important part. And the primary outcome was the coupling of an atmospheric model, WRF, an urban surface model, Princeton UCM, in a subsurface model, PARFLOW, in addition to improvement of these components and applications to study a range of urban challenges. So just a few days ago, Mahdat Talibpour, who is working with Claire Welty and myself, we are the PIs of this project, got the good news that this paper is now the paper that shows essentially that if you couple the surface and the atmosphere to the subsurface, or if you do not couple, you're going to get a very different answer from the model. So in this figure, what we're on the left is the WRF UCM, so atmosphere and surface without the subsurface. And this is the field of soil moisture over a domain near Baltimore. And on the right is the same simulation, but now coupling with PARFLOW, coupling to the subsurface. So what you would notice is that when you basically look at what's happening beneath the surface or what's lurking beneath the surface, on the right, you see a much more moisture near streams, as the subsurface redistribution of moisture basically takes water there. While on the left, without this redistribution, you see a much more homogeneous and variable field of soil moisture. Now, what this paper basically establishes is that the coupling is important, And from here on, what we're going to be doing is basically showing how, for example, use versus an uncoupled model will actually influence the some conclusions and some suggestions or recommendations you might do for cities about how to basically mitigate urban heat islands and basically use hydrology to their advantage, if you want. So the implications is that cities need to consider the connectedness of the impervious cover and the use and properties of engineered soils. So it's not only what you put above the surface, it's also what you do below the surface that's going to impact how your city responds. So this is nice. It came at a timely time, if you want, because basically this is the first paper that comes out of this full coupling, which was the aim of the project. But along the way, we've learned a lot. And so I've been working on UHI problems for the last 12 years, 6 of which through UN. And so for this talk that's kind of geared towards decision makers and stakeholders, what I'm picking is, so you want to cool your city. And what I want to go through is a series of questions that I think people who are thinking about how to actually implement these cooling measures in cities should think about. They develop the plans and as they implement these plans for how to cool their cities. So my first question is why? Is it because this is just a trend and everybody is talking about UHI being a bad impact and that we need to combat it? Or do you have some tangible data that basically heat deaths are increasing in your city and you want to mitigate that? So the reality is most cities in the US are in cold climates where the heating degree days are larger than the cooling degree. So in terms of energy consumption, you're driven by heating, not cooling. And cold fatalities are larger than heat fatalities. That's most cities, not all cities. And the reality is the UHI have some wintertime benefits. And this paper we looked at, for example, the UHI signal during a very cold wave in 12 cities, I want to say, or about 12 cities. And you see that during the day and during the night, these cities were hotter than the rural surroundings. This is the difference in temperature between the rural areas around it. It can reach up to 4 degrees or even 5 degrees at night. This is the air temperature. So UHIs have wintertime benefits. And if your city is very cold, like Boston or Minneapolis, then you really have to think about how to approach the question of combat. Of course, the answer is in Phoenix or Miami. Now, don't quote me as trying to tell you that basically the UHI is a good thing. It's not your friend. But what you need to think about is, what is my climate? What is it like? Am I in a more cold or warmer climate? What is the expected hazard going with climate change? Is there a significant shift from cold to heat hazard in terms of health impacts or in terms of heating and cooling demand? So you need to think about where you are today and where you're going to be maybe in 20, 30 years with climate change. And you want to look at the extremes, not only the averages. Also want to compare the summer wintertime UHI in your city stronger, and which one is stronger, and the seasonal cycles of the UHI very much depend on the seasonal cycle or the annual cycle of rainfall and radiation, as we basically established this paper. So if you have wet summers or dry summers, the answers to all these questions will actually be very different. You want to also consider urban temperatures, not only the difference between UHI and between rural and urban, not only the UHI. So what you care about is the actual absolute temperature or Celsius or Fahrenheit temperature. And you want to focus on those and combat extreme heat, not only combat a temperature difference between cities and surroundings. You also, if you are thinking impacts or financial impacts, you want to ask the question, what is more expensive in my city? Is it heating or cooling? and which one is more carbon intensive, the answers are often very different between different cities and between heating and cooling. So the bottom line is when you try to think about heat mitigation strategies, you also, if you're in a cold climate, you can think about mitigation strategies that may not affect the wintertime UHI, allowing the wintertime UHI to remain strong and basically giving you all the benefits. But measures that also, while they in the winter, they might very well work in the summer to basically mitigate urban heat. For example, ground-based green infrastructure will have very of wintertime UHI because mainly it provides evapotranspirative cooling, and that's going to be small in the winter. However, it's going to work very well in the summer because again, evaporative cooling is going to be very strong. You can also think about, for example, for your roof, thermochromic skins or other material that will change color to be darker in the winter and lighter in the summer, so the fraction of the solar radiation they absorb might be different. Again, we showed this in this paper from 2019. So you know, you asked all the why questions. Now you want to also think about which UHI you are talking about. So you can consider urban temperature and their differences relative to rural ones at the surface. So this is what we call UHI. In pedestrian level or in air above, probably the air above, you don't care about it. You also can consider the subsurface UHI, and as we showed recently, you should probably be considering hydrological UHI in your water bodies. And these are very consequential. Let's take the surface and air UHIs because these are the ones that are people focus the most about. They're quite different. So the air UHI is much smaller. It would be, you know, 2, 3, 4 degrees, maybe. In some cases, it might reach more than that, but typically it's less than 5 degrees Celsius. It's going to be much more homogeneous than the surface UHI. And the air UHI mostly peaks during the nighttime when urban surfaces are releasing all the heat they store during the day. So peaks at nighttime. If you consider surface UHI, let's say measured from satellite, it's going to be much larger. So you can have 30, 40 degrees between the cities and the rural evaporating rural areas. It's going to be much more variable in space. It can, you know, the surface temperature can vary at the scale of a meter. And unlike the air UHI, it's almost always invariably stronger during the day, where solar insolation create big differences in the response. So which one you consider is also related to your goals. So air UHI is going to be more important for cooling demand because basically leakage through building is or you know, an intake of fresh air for cooling is a big contributor to cooling electric demand. So air UHI is important for that. For thermal comfort, the surface UHI be at least equally important when you think about the radiative loading and on the body, which actually the radiative loading might be larger than the convective loading, that the heat that you gain from the air around you. And again, we looked at this in this paper to show that basically, let's say sometime if you use white walls, you think you're cooling the city, but the pedestrian comfort will be much worse because the white walls are going to reflect so much sunlight onto the pedestrians and making them really uncomfortable. Again, if you're thinking, you also could consider the hydrological UHI, so your aquatic system and water quality. If you're interested in that, you might want to look directly at the hydrological UHI instead of the air or surface UHI. This is an example of the hydrological UHI. This paper is currently in review, where basically we show the temperature surges when you have hot runoff falling on urban pavement, or rainfall falling on pavements and extracting the heat and creating hot runoff. So these are surges of temperature that can reach up to 10 degrees Celsius in this case. And you would see that in the afternoon, when the surface UHI is stronger, as we said, basically, if you get a rainfall, you're much more likely to create these hot flashes, basically, in your streams that might damage your aquatic system. So that is, as with atmospheric UHIs, cities actually have a hydrologic UHI that's driven by similar land use and land cover alterations, and both can be mitigated by common measures. So we talked about which UHI. Now let's ask the question where. The UHI is not a constant parameter in space. It varies over the whole city. We said that the surface UHI can vary at the centimeter scale. So what is your goal space-wise? Do you want to have an average cooling of 1 Fahrenheit in the whole city? Or is your goal to basically reduce some severe overheating problem in the urban core? And it might be in the urban core. Some cities, actually, the hottest temperatures are not in the urban core. They might be in some close suburbs that have that are very industrial and have very large parking roof and little vegetation. You also want to consider how variable is the UHI in your city. Is it strongest, for example, in poorer neighborhoods that have little tree coverage? And this is, something that we observe in almost all American cities. Poorer neighborhoods where the income is lower, they have basically lower housing prices, and they tend to have less green cover and less ecosystem amenities. So do you want to use UHI as a tool for increasing equity, or are you approaching equity differently? And how are you approaching environmental justice? Where is your UHI and where strongest, and where do you implement mitigation measures becomes important? Where are the pedestrians most concentrated? So do you want to target areas where basically you have pedestrian street and businesses that basically you want to provide a shade cover so people can still come out during hot days and basically not be fried, still enjoy their time outside in these areas and still support these businesses? Are some areas near large water bodies? That's gonna be important because the land sea breeze means that they are better off during the day as you get a sea breeze, but they may be worse off during the night when you get a land breeze, because now they are downwind of the whole city and all the hot air from the city is coming towards that coastal area. Where are the surfaces or areas you can intervene in? If you map your city, how much roofs can be made cool, white, how much can be made green, where are the areas that you might add ground vegetation, and so on. And this is an example of how these questions can be addressed. So in this study, what we looked at is doing green or cool interventions to cool Manhattan. So the question was, how can we cool the urban core of New York, which is in New York quite hot? Jersey City on one side and Brooklyn on the other are equally hot, but Manhattan is pretty hot. So how can we cool the urban core? And we said, okay, we can implement green or cool infrastructure. And we can do this over the red area, so over that urban core that we are trying to cool, over the whole 5 boroughs of New York, or over the whole metropolitan region, trying to basically implement green roofs. So for example, we said that in any of these 3 intervention scales, we're going to convert 25% of our roof to green roof, and they're going to be evaporating at 75% of their potential rate, because this area is wet in the summer, and so we assume that there is gonna be sufficient moisture for these roofs to basically evaporate. If a roof dries up completely, if a green roof dries up completely, it doesn't give you any cooling benefits. So the answers we got were interesting. So again, this is the cooling over a number of days. The red is for the intervention in Manhattan. The green is for the intervention over the 5 boroughs, and the blue is for the intervention over the whole region. And you can see that in this case, where you basically, when you cool the area around the city, you benefit quite a bit. You get doubling of the cooling from about 0.7 to about actually from about 0.8 to about 1.6 degree cooling if you cool the area around the city, because these are the areas that are preheating the air that goes into your city. So in New York, increasing the intervention area was very beneficial. But also you note that this cooling varies drastically between a day and the next, and I'll come back to this topic. So the cooling benefits are not steady in time. Now, the answer was different when we looked at Phoenix. So Los Angeles, you see that also when you increase the intervention scale from the urban core to the whole region, you get more cooling. Phoenix, you got cooling, but it hardly mattered when you increase the intervention scale. And the reason it turns out is that Phoenix core area that we were targeting for cooling is at the edge of the metro area. So it's upwind of the rest of the city. So basically, if you, it could be from the rest of the city in many occasions. And so if you cool the rest of the city, you're cooling the areas downwind, then you don't get the same benefits. So the conclusion is that mitigating UHI using cool or green roof require a high penetration rate, and you need to basically consider the geography or the wear in your city. Another question is when. Again, we said that surface and air UHI have different diurnal cycles, so the surface peaks during the day and the air UHI often peaks at night. So which one are you targeting? Do you want to make the whole summer more pleasant, or are you interested in focusing on mitigation of overheating during heat wave periods, during the extremes? Obviously the answer I would suggest is that you look at the extremes, not the summer more generally. What is the timeline over which you want to obtain results? And as I showed in the previous slide, don't expect consistent result from your mitigation measurements every day. This is an example again. So if I go back here, again, I told you that the cooling benefits, let's say over New York, were very variable. And even without intervention, when you ask the question of when, you notice that in this simulation over New York, if you look at the urban and rural temperature separately, you'd notice that on this night, you had a 2-meter air temperature difference of about 8 degrees between the rural areas and the city. And if you look during the daytime, a couple of days later, actually 1 day later, you had a urban cool island in this case. So the rural areas were actually hotter than the city. Overall, you have an urban heat island signal, but hour and day to day, that signal can be very large, can vary drastically. It can flip to become an urban cool island, and it's certainly different during the day and the night. So basically, you want to consider the time variability of your signal. And in that sense, the average UHI does not exist. Average person in a statistical population does. You really have to account for variability in your design. Another question is, okay, you want to cool your city, how? What are the measures you are considering? So trees and tall vegetation are going to give you a very different set of benefits from your short vegetation. Trees can offer shade, short vegetation cannot. Also the cost and maintenance effort is quite different. Are you thinking about evaporative cooling without vegetation, just by, let's say, irrigating pavements or water bodies or something like that? Are you consider reflective surfaces like cool roofs? Are you thinking about reducing your waste heat from cars and air conditioners, for example, through electrification of the car fleet or through the use of evaporative cooling towers instead of your air-cooled AC? Are you considering changing the materials, for example, reducing the use of concrete, which stores a lot of heat? And what are the co-benefits for each of these? And, again, what I learned over my journey with studying the urban heat island is you really should consider a portfolio of measures. There are no silver bullets, just like the idea of the wedges, the concept of wedges for mitigating greenhouse gas emissions that were actually introduced at Princeton by two of my colleagues here. If you think about reducing the UHI, you have to think about wedges and portfolios. So if this is the baseline scenario where increasing regional temperature lead to increased urban temperature linearly, you want at least that slope not to be larger than 1. You don't want the urban area to heat more than the region. So the red slope, you want to make it less than 1. And let's say you start with 1.2, a slope of 1.2, you want to reduce it to 0.8. You probably need interventions: green roof cover material, retroreflective facades or cool roofs, smart irrigation maybe during the hottest days of the year. When you have extreme heat, you can think about the mister David was talking about a couple of weeks ago. You can think about parking, so park irrigation or other measures to evaporative cooling. Another question about the how. So, what is the what's your data analytic or modeling capabilities? Are you working with a university that can do fancy work simulations, or do you have to do do this work with much less information? I love this graph, so I'm going to show it. When you think about models or analytics, you can think about 4 classes. So descriptive analytics tell you what happened in the past, but doesn't tell you why. It just told you, you take observations and you say, in the past I had a heat wave or a strong urban heat island. Predictive models tell you what can happen in the future, so you can forecast that you're going to get a heat wave in a week. Diagnostic models can also tell you why something happened. So I got a heat wave maybe because there was a high pressure system and meandering in the jet stream that basically prevented this high pressure system from moving very rapidly. For the UHI, that I have a lot of asphalt in the city, so I have a strong thing. And what you really need for kind of designing mitigation measures are what we call prescriptive models. This can tell you, how can I make it happen or not? So basically, you want models that allow you to have, for example, realistic scenarios about green roofs in the city. It's a model that can only do 100% green roof conversion. It's not useful because that's not realistic. So you want a model that can tell you, okay, I can convert 15% of my roofs to green. I can add, 10%, or I increase my ground vegetation cover percent. I can do this. So ideally, if you have access to prescriptive models, they can be very useful in designing your plan. Finally, a final set of questions is, who's doing this mitigation? Who is most at risk from current UHI? Who would benefit the most from a proposed mitigation strategy? Who's most excited about the plans? Who will pay for it? And can you find free volunteers, for example, like the school roof program in NYC, that basically get volunteer people to basically go and paint roofs white? So they find buildings who want to basically change the color of their roof, and they team them with volunteers. All they pay for is the paint, and the work is done. Who will implement it, and who will monitor the progress and the benefits to basically establish that whatever effort the city expanded basically was worthwhile. So finally, I just want to thank all my long list of students and collaborators and postdocs here, and my collaborators from outside of UN here. They did all the work, and I just get to kind of present the results and pretend I know a lot. So thank you very much. And with that, I'll stop here, exit my slides. And if you have any questions, please go ahead.
Great, thank you, Elie. I don't think you have to pretend to know a lot. I'm pretty sure you're a very brilliant man. We did have one question come in from Alex. Alex, do you want to say hi to Elie and turn your mic or camera on?
Okay. Hi, so this is totally probably out of scope. Oh, just to introduce myself, I was a new AURP alumni from 2019. And now I work for GHD in sustainability consulting, but my background's in civil engineering. So this is probably a little out of scope, but I just wanted to put it out there because I think it's important to the conversation. Does some of this UHI mitigation, such as vegetation, increase property values and risk displacing poor residents? And does that kind of cancel out the equity implications? I know I'm just like hyper focusing on that one side, but I just wanted to know what your thoughts were.
That's a fantastic question. I don't know the answer, but I can tell you, that basically, yes, adding green infrastructure and ecosystem amenities does raise the price of houses. This was actually established by some colleagues at Ohio State University, with whom Claire Welty and I were working through the predecessor of UN, if you want, the WSC water and climate. I forgot the acronyms, but basically, so we had some colleagues who looked at that, and certainly in neighborhoods where basically you have more trees and ecosystem amenities, the housing prices are higher. They don't go up 20%. And so basically, I think the increase in the house price is not going to be drastic to the point where it will really change the market dynamics. But that's a guess, so don't quote me on that. But the increase in the prices were moderate, like in the single-digit percentages. And so it's not a big one. And so the other way to think about it is that, you can do interventions, in such a way that you don't increase well, I mean, in a way, yes, it could in a way, if you add parks and other things, it might, and depending on the housing market, it could increase it a lot. But you cannot say, okay, I'm gonna keep the poor neighborhoods with very few amenities to make sure they don't, housing doesn't become more appealing, because now the people are living there. If that increases the housing price and they sell it and go somewhere else, maybe that's good for them. So in a way, even if there is this risk, you cannot try to improve the ecosystem amenities in poorer neighborhoods. Even if that risk exists, you want to think about how do you mitigate that risk.
Thank you.
Great, thanks. And thanks, Alex, for staying connected with us. It's really great to see some of our former ERP students still connected. It's wonderful. We did.
I see another question in the chat, or we can take raise the hands and then go to the chat, or how should I do this?
Why don't we start with the chat? I'll just roll with the order in which it came in.
So the question is, you saw that adding the subsurface changes subsurface hydrology. Does it impact surface and atmospheric temperature? Yes, it does. I didn't show it here, but certainly the surface temperature, the evaporation, the latent heat flux, and the sensible heat flux were all modified by the change in soil moisture. So it's kind of up the chain. Once you change soil moisture, the evaporation and everything else will change. So I just showed that, but yes, it does impact all the other parameters.
Great. I think we'll go to Sharon next. Sharon, do you want to turn your mic on or camera or both?
Okay, there's both. So thanks. This is really enlightening presentation, Elie, and I appreciated the question about equity. I just wanted to add one thing here when we're talking about cities and gentrification. So a lot of times it's not just a single family homes turning over, right? This is really a matter of large scale development, developers coming in and transforming whole neighborhoods from, maybe low-income housing into high-end condos or, apartment complexes with, all these accoutrements that, upper middle class people like to live with. So the equity question, you're right, that's a great question, and it's complex. And it means that this is something that, people who are concerned with urban planning and heat don't just control, but it involves, city politics. So I just wanted to put that comment in for the record. Thank you.
Thank you, Sharon. Yeah, absolutely. I thought Mary had a question, but maybe not.
No, I did, but I wanted to lower my hand. I've actually a comment and a question. My comment is that I think, as Sharon pointed out, that this is the gentrification issue is a very complicated issue, and I liked what you said, Elie, about the need to improve all neighborhoods and provide cooling and greenery, even for people with lower income. And I think that the solution to this problem is maybe raising the income of everybody so that people can afford housing, rather than, oh, let's make sure to have some really terrible housing that nobody wants, so we've got a place to stick the poor people, right? That's not a solution. That we shouldn't be satisfied with that. But these other kinds of solutions, they require this interdisciplinary kind of interaction with people from sociology, from economics. It's not something we can solve with engineering. But my question is, this is amazing, these coupled models with the groundwater, the surface, the atmosphere. How do you manage error propagation as you're coupling these models?
So that's an important question. So we haven't gotten to the point where we kind of are actually validating the model extensively. So the first part was kind of model verification, if you want, and evaluation. We didn't get to that point, but so the problem with all these sorts of models is that if you let the model run for a long time, it's gonna drift away into its own weather realization. So weather is a chaotic system, and so if you if you're trying to forecast weather for tomorrow, what the weather forecasters will try to do is keep assimilating real data to anchor the initial conditions. So as you run your model into your initial error is very small. So as the error grows in time, it will not grow too much. So if you the question then becomes, okay, if with or without par flow, what is better? Should I, let's say, worry about par flow subsurface error propagating to the surface and then influencing my surface? Possibly they surely do, but the alternative is worse. Like the alternative is basically to say, so the error in par flow, maybe the three-dimensional subsurface flow is not accurate, or it has some errors. But that is still much better than saying there is no subsurface flow. So the default option is pretty bad, that even if you have a model coupling and propagation. The other thing that is good is that the subsurface and atmosphere have different time scales. So when you have two different time scales, the error propagation is there's not going to be, let's say, resonance of error. So it might you might be in okay shape. But again, that's hand-waving argument. So yeah. Now, there was a very interesting question in the chat about electric vehicles for reduction of heat emissions. So this turns out to be the proposal that I was talking to Sarah that we're just submitting today about basically this new emerging mobility in cities where you have kind of automation, electrification, sharing, and micro-mobility. And so if you think about their combined effect on cities, it's going to be quite drastic. So electric vehicles will basically stop emission of pollution and heat in cities. Automation and sharing, if they reduce the cost and the ease of travel, might lead to sprawl and increase in travel. So they, on their own, they might actually be problematic from a sustainability perspective. But sharing also would allow you, if everybody used shared taxis, would allow you to move around the whole cities at the same way with 10% of the car fleet, which means you need much less parking and much less, basically, all the carbon embedded in the cars. And micromobility is very important in many ways. So when you think about all these kind of combination of this kind of emerging mobility and what impact it will have on cities, I think it's going to be the biggest disruptor of cities in the next couple of years. I mean, electric grids are going to change drastically, but you're not going to see it that much. But the change in transportation is something that's going to affect space use, electricity, carbon, heat, pollution, and in many ways is going to be a big disruptor. So hopefully I'll be able to tell you more if we get the grant and can work a little bit more on that.
And yeah, there was a follow-up from Tom that I think probably was just addressed, but Tom, feel free to pipe up if you have anything to add there.
So the direct heat from automobiles is not a main driver of urban heat islands. It's a secondary driver, but it is it's not in a crowded, busy street in Manhattan. Its impact at the pedestrian level is going to be significant. So at the city scale, it's probably not, but at the single street scale in Manhattan with, traffic jams, it becomes more consequential. So it depends again where and when. This, are you asking this question? So to be able to answer it. Let me see. There was. Okay. So is there a model for taking out the addition of electric vehicle and reduction in combustion? Yes, I mean, this is kind of, some people have done some of this work, but there's still much more to be done and learned. So then we have the comment of Tom. Are the suggested uses of these models more predictive or prescriptive? For example, can they enable an understanding of process to help make suggestions? So prescriptive models are by kind of almost by construct that have to be predictive, right? Because if you want to decide whether, if you want to plan how to avoid some outcome in the future, you have to be able to predict the future, and typically to project and prescribe, you have to have a quite an understanding of the physics to construct this model. Does that answer the question? I guess.
Yeah, I think Ben's microphone is not working, so I'm sure he'll pop something in the chat.
So, yeah, but basically you want models that allow you to basically understand processes. But there's an important way in how do you use models to understand processes. So if you have a process that is parameterized in your model, you should be careful with using the model to infer something about the process. So, for example, to give you an example, I mean, in these models, we prescribe, let's say, prescribe, for example, how albedo influence the amount of heat that is absorbed by a surface. So in that way, all the complex radiative processes at the surface are being parameterized with this simple model of an albedo. So you cannot, from this parameterization, I'm giving a gross example, right? You cannot, from this parameterization, go on to talk about how processes interact with radiation, because your model, this process was parameterized. So you want to look to use a model to understand the physics, you need to focus on processes that are resolved in the model. For example, subsurface redistribution is resolved by power flow. So we can say, okay, given that, I can use power flow to tell me something about subsurface redistribution. However, what's not power flow is the hydraulic conductivity of the subsurface. It's imposed. So I cannot, using power flow, say how the grain structure is going to influence hydraulic conductivity. So again, make sure that you don't use, you don't try to infer something about the physics of processes unless these processes are actually resolved by the model.
Okay, thank you. And then Alex chimed in with another question that's in the chat here. So do you think energy reductions from cooling in the city by using vegetation outweigh the energy costs of importing water in places like Los Angeles?
So that's a good question. I don't know. You would need to do kind of a life cycle assessment on this question. So the other possibility is don't water for irrigation for LA from Colorado. So another paper we worked on through this project is about using seawater for cooling. So you can actually extract seawater, salty water, brackish water, and irrigate it and let it evaporate. Now you cannot irrigate plants with it, but if you think that evaporative cooling is what you're after, you can just have sand roof, irrigate those sand roofs with salty water, and you're going to get the benefit. Now, of course, you're going to need piping systems to bring salty water to roofs. But these questions, to really answer them, you need kind of a life cycle assessment of this question. But certainly, if you're in water poor areas, you need to think carefully about your water use for this. And another paper I should mention is a paper by Jiwa Wang, who was involved in the project early on, and but not in later years. But they had, and actually with Joshua Yang, I think, who ended up being a postdoc in my lab. What they tried to do is basically look at the benefit of maximum water, so just cacti and nature, basically native plant species in Phoenix. So very little water use, but not a lot of heat reduction, versus basically maximum heat with large water uses. And they looked at that trade-off in Phoenix, and that paper is available. I wonder if that are linked to. But yeah, those are trade-offs you'll have to consider at the city scale.
Yeah, and I did just drop in the chat queue the link to our Zotero database that has all the UN reported publications, in case anybody wants access to that. So Ben had another follow-up for you in the chat. I'm wondering if the gain in process understanding may be the most helpful part of the model, which may inform other predictive methodologies. For example, should spatial distribution of green space be considered, or simply the total area of green space? If spatial distribution is important, then maybe we could somehow include a parameter capturing that parameter in a regression model or something similar, which may be used for prediction.
Yeah. So again, process understanding, you cannot construct predictive and prescriptive models without process. Because when you are forecasting something into the future, you need to have a mechanistic or I guess you can have a statistical. But let me take this back. You could have a predictive model that has very little physical understanding or process understanding by just kind of statistical projections. But prescriptive is more difficult. So prescriptive, you want the model to tell you, if I change from asphalt to green roof, okay, or green area, what will happen? So it's kind of assumed in that you know the physical difference between how asphalt absorbs and retains heat and dissipates heat versus a green infrastructure. So a process understanding is a prerequisite for constructing these models. Specifically for that question that you asked, yeah, it's definitely true that that spatial distribution of green infrastructure is as important as total amount. So or comparably important. So you want to decide where you're putting this infrastructure, not just the total.
Great, thank you. Let's see. Thank you, thumbs up. Okay, well, I haven't seen any other questions pop in, so I will be sure to send out the link to the recording. Thank you so much, Elie, for your presentation and great discussion points as well. Be sure to tune back in next week. We're gonna travel down to Arizona State University and hear from Dr. Georgescu there with kind of a complimentary presentation from your work, right, Elie?
Yeah, absolutely.
Great.
Again. Bye-bye.
Okay.
Thanks, everyone.
Thanks. Good luck with the proposal.
Thank you. Bye.
All right. Take care, everyone. We'll see you next week.